Okay, good morning. First, let me thank the organizers for inviting me to this historic event. It's 65, one reaches 65 only once in a lifetime, which I don't think anybody would dispute that. And the title of the workshop, the Information, Decisions, and Networks, really beautifully captures Demos's contributions and powerful research over the past 35, 40 years. It's, I have several connections to Demos. The latest one was Ashutosh, who was a postdoc of mine, and that gave us an opportunity to, in fact, co-author a paper, which I'm quite proud of. After 35 years, we finally wrote a paper together. And I'm not sure exactly when I met Demos, but which CDC was the first one you attended? I think it was at one of the CDCs in the 70s, late 70s. And then I, of course, in the early 80s, I was a reader of his papers, and I, in fact, handled some of them as associate editor, and the decentralized vault problem, and the asymptotic agreement, and so on. They were ahead of their time at the time, and definitely inspired many follow-up work since then. And we have seen all his former students last night, for those of you who were there at dinner, quite passionately talked about him. And one thing that was missing was a birthday cake. So here I have it with 6 candles. It's a virtual cake, so you can blow the candles, Demos. And again, the congratulations and the happy 65th birthday. And again, some of the former students said that they would go to his office with books, so that's why I put here some books in different colors, because we heard that there was organizing the books on the bookshelf. Barbara used some color coding, and so this is what you have. Now, I wanted to pick a topic which definitely matches Demos's contributions and interests, and what his students have worked on, at least most of them, over the years. And I should say that one common point between Demos and myself is that I don't think he would dispute that we are both devout members of Witzenhausen's fan club. And we had, over the years, many discussions on the Witzenhausen's papers, and when at a time when not too many people actually were interested or cared about it, it was ahead of its time. Everybody will, but now more and more members of the community are actually talking about those papers and the insights behind them, and more importantly, the alarms and that they provide, if you want to extend control theory beyond its traditional boundaries. So yesterday we had some mention of strategic information, so I again wanted to pick something which will interest Demos. We found out that one advice that he gave to students was make sure that what they are working on is interesting. And I hope, Demos, you'll find this an interesting problem. And it is a fairly, on the surface, a fairly simple model, but it is rich in terms of the concepts and what it brings to the table, and as far as the future work goes. So here we go. First, let me say something about the non-strategic communication, and this is the classical framework of Claude Shannon, and the fundamental problem of communication is how to reproduce at one point, which is the destination, either exactly or approximately a message selected at another point, which is the source. So here is your diagram, and I'll have this here because everything will center around this seemingly simple configuration. So this is the transmitter, and this is the receiver, and here is a source, and the source generates random variables. This could be, I'm going to concentrate on the case when there is a single random variable, so this will be a one-shot thing. But the communications theory, of course, the Shannon's theory deals with a sequence of X's, and you have to encode them. They go through a channel which, with some description that the probability of Y given the output of the channel, given the input is known. In this case, it's the disturbance, let's say Gaussian. And then you, on the receiver side, you have to decode it and generate a U1, and you want U1 to be as close to X as possible. So this is the traditional Shannon's framework. So there are two basic assumptions, and I'm going to depart from these assumptions in the strategic case. The first is that the transmitter and the receiver, they have identical objectives. So I'm looking at this as a general stochastic control problem, if you like. And so there are two decision makers, or this is a two-stage control problem, where you have G and H. And it's a problem with non-classical information in the sense that the H who acts after G does not know what G has access to, doesn't share the information that G has. So you can look at it as a two-stage control problem, and with some appropriate modification, the Witzenhausen's counterexample would also fit this into this framework, and I'll say something about that shortly. But the important thing is that it's a team problem. It's a cooperative optimization problem where a certain distortion measure is minimized jointly by T and R by picking these mappings G and H. Think of this now as a single shot problem. So the other assumption is that the transmitter and the receiver, they know all other mappings and the statistics while they do this optimization. And so, for example, they share a code book. Now, one special case of this is when X and W are independent random variables. This is a more sort of a traditional formulation. U0, U1 are real valued actions, if you think of this in the context of two decision maker problem. And this is you introduce an objective function, which is a function of Q, is a function of X, U0, and U1. And then you minimize the expected value of this, given that U0 is G of X and U1 is H of Y. So this is a joint minimization problem. As a standard distortion measure, one takes a quadratic distortion. Let's say that these are all Gaussian random variables, so U1 minus X, so you want U1 to be as close to X as possible, and then you have a soft constraint on U0, or if K is equal to 0, then you add a power constraint on U0, expected value. The variance of U0 will be less than or equal to some given constant alpha, which is common knowledge to both. So what is strategic communication now? I'm going to modify this. I'm going to relax this assumption of the two boxes G and H having the common objective. So the receiver still wants to estimate X, but there is an additional variable here, theta, and this is private to the transmitter. Theta is not shared by U1. Theta and X could be correlated, and in general they are going to be correlated. So there will be some information which will be relayed to U1 through this transmission. But this is private. The precise value of theta is known only to the transmitter, but is not known to the receiver. And so theta actually constitutes a bias term here. While the receiver wants to be as close to X as possible by choosing H, what the transmitter wants to do by choosing H, by choosing G, to be as close for the outcome to be as close to X plus theta. So theta is a bias term, but this bias term is known only to the transmitter. So this is the strategic communication. Let me discuss some applications. I mean, we see this all the time. You convey some information to the other side, but you don't tell the full truth. You want the other side to think that it's actually the real state of the world is different from what it really is. And so here is one example. This is a current topic, environmental, climate control, if you like. A senator wants to vote on a bill, and there's the state of world X, and then asks a scientist and the opinion of the scientist, what's the state of the world, and the scientist, for whatever reason, gives a biased opinion. In fact, gives an information in such a way that the senator will think that the state of the world is not X, but X plus theta. And a second one, which is, we are all guilty of this when we see our medical doctor and the questions are asked, and we don't, there is some issue of privacy, and we never tell the truth. I mean, there is a slight distortion of what we are, how many glasses of wine we are drinking, and so on. I don't think anybody has ever given the correct information to their medical doctor. So the doctor is asking for medical information to arrive at a correct diagnosis, but the patient is really concerned with her privacy, and that's the theta in this case. This is, in the legal cases, a prosecutor wants to go for a guilty verdict, but there is some real state of the world, which is whether how much he knows about the facts, and then he may distort that fact, and this is known as Bayesian persuasion. He wants to persuade the judge for a guilty verdict, but the judge actually wants to know exactly what X is, but the prosecutor again gives a distorted message. Now, the latest, the last application is this crowdsourcing application such as Waze, and this is very commonly used. The people living in a city are generally asked to provide information, for example, on the state of congestion on their street. And they say, okay, congestion level is high or low or this way. And there is, again, a bias in the way this information is transmitted. For example, if they don't want traffic to congest their streets, and if it's a quiet street, then they say, oh, there is congestion, so that the traffic would not be routed in that direction. Whereas the business would like to see more traffic coming in, so they would give another distorted sort of message. And this actually has happened. The Miami cops are falsely reporting, this is from the Miami Tribune, their locations on Waze to trick drivers so that they can, this is towards the end of the month, so that they can have issue more tickets. And then another one is cyber attacks. The Technion students, this were created a cyber attack on the as far as the traffic goes. But this is interesting. This is from Los Angeles Times. This is precisely what I was saying. The residents' outrage after Waze app used to avoid traffic ends up sending Los Angeles drivers down once a quiet, hidden street. So they tried. Some of them tried to send information on fake accidents and so on, but it didn't. There were very few of them who were doing that, so it didn't help. So anyway, so in real life, we have this situation. People, when information is transmitted, and even if there is a common objective, there is some slight variation on that objective, and the bias term comes in. So in the strategic communication, we have essentially, so instead of a common goal, a team problem, we have a game, because the cost functions, the objective functions are different for the transmitter and the receiver. And when you have a game, then you have two possible approaches, and one can actually show that this game is not strategically equivalent to a team problem, so it's not a trivial one. And so you can have Nash equilibrium or Stackelberg equilibrium. So the difference is that the Nash equilibrium is one where the players are symmetric. The players in this case are T and R, and you are looking for an equilibrium such that when you fix T at that equilibrium policy, then the minimizing R, the R minimizing JR would end up with the equilibrium policy, which is part of that pair, and vice versa. So here is a precise formulation of this. Note that this is a problem with non-classical information again, because the R does not have access to what T has, and so it's not a very standard static game problem. So this is the Nash inequalities, and note that as I was saying here, the Y depends on G at equilibrium, Gn, and whereas here in 2, the Y depends on G, not the Nash equilibrium value. So the interest is to find Gn and Hn, which satisfy this set of inequalities. And the question is, does there exist one? What's the structure of that solution, and is it unique? Okay. And the Stackelberg one probably makes more sense in these scenarios, is one where the T, before announcing a policy, and that policy will be a function of x and theta, will take into account the response of the receiver. And so that's the response of the receiver is given by this, and note that it's for all G in this case. This is H star G is the best response of the receiver to an announced policy G, and then the transmitter will have to minimize this with respect to G, and that's the G sub S. Okay, so this is a non-zero sum game. So going back to, because I want to tie the two problems, the non-strategic one and the strategic one, and the difference is that there is this presence of theta, which is private information, and the presence of theta converts the team problem into a game problem, and then you have essentially a bifurcation depending on which equilibrium solution concept you take. So I'll be talking about Gaussian random variables, because this is bread and butter for our community, and so X is a Gaussian random variable, 0 mean variance sigma x squared. W is a Gaussian variable also, independent, And this is the standard, this is probably the simplest problem in communication. You have a quadratic cost function, the quadratic distortion measure between U1 and X. And again, this is a problem with non-classical information. If you try to sort of dynamic programming definitely does not work. And if you want to use the standard sort of calculus of variations and it's highly complicated, you don't even know whether the G and H are smooth, for example, the optimum G and H. A priori, you don't know that. So, but surprisingly, in this problem, the solution is actually, this is known as the Gaussian test channel, the optimal decision policy, that is the best encoder and the best decoder, even though it's a problem with non-classical information, is linear. And the only way I know of proving this is using information theory, the channel capacity and weight distortion function bounds. And this is the mutual information, this is the data processing inequality, and the mutual information between X and Y, two closer random variables, is larger than the, farther away, is larger than the mutual information between X and U1. X and U1 is farther away. Okay, and then you do your find bounds on this quantity, you find bounds on this quantity, and then you end up, and those bounds are actually the channel capacity for a fixed power level here, and for a fixed distortion level, this is the rate at which you have to transmit in order to achieve this distortion. So this gives you an inequality between channel capacity and R. If you can make this an equality by a particular choice of a policy, then you are home free. And so that this gives you a lower bound on beta. You cannot do, the distortion cannot be any lower than this, which depends on the power level. And so the last step is to show that there exists a linear policies which will achieve this with an equality. So that's the only way to obtain the solution. So it's a problem with non-classical information. Now, if you consider a much more general, this is as a side remark, much more general quadratic cost function, quadratic in U1, X, and U0, but if you have a cross term between U1 and U0, then this converts into Witsenhausen's counterexample, and the optimal solution is not linear. So if you look at the general sort of this exactly the same problem, the only difference is that you are looking at a family of these problems where the Q is a general quadratic function. So depending on whether there exists a cross term between U0 and U1 or not, you have two completely different solutions. And so the Witsenhausen's is, mind you that there is, it does not have a linear solution. The solution is nonlinear, but the exact form is not known. But it's not quantized based. So one of the few instances this actually constitutes, this is essentially the Shannon's theory, but Shannon's theory generally requires sequence of random variables, and sometimes the encoding involves delays and so on. This is a case where one of the few instances where a one-shot problem can be solved using Shannon's theory. Okay, this is where C alpha and R beta are. So now the question is, does this extend to strategic setting? And when we bring in a theta. So the strategic setting again is this, and X and theta are correlated, private to T, and the R has a different objective as I have given here. So there's a very nice, very influential paper in economics, in information economics, which is by Crawford and Sobel, appeared in Econometrica in '82. They looked into this problem, but without the channel noise, without W, and they looked at it when theta is not random. So the bias term is, so if it's not random, it means that it's known to U1 also. Okay, so it's not very in the application settings that I discuss. This does not make that much sense. It's not very relevant. The random part is I think more interesting, and in fact the results in that case are more interesting. But this is a starting point, and so they looked at this problem with these assumptions and they solved it completely. And afterwards, thereafter, they're not the ones who coined this word. It was called, this class of problems were known as cheap talk. Cheap talk because there was no cost on communication. There was the W was not there. It's noise free and no power constraint and nothing. And it was, I believe, Farrell in the Rand Journal of Economics in 1987 was the first one who actually coined this cheap talk, and it's known as cheap talk now. The noisy version of this was later discussed again with no channel noise and theta with channel noise, but theta not random, and it's called noise talk, so cheap talk to noise talk, and Bloomberg and Kawamura in theoretical economics in 2007. So from 1982 to 2007, quite a number of years, several decades. And this is a very active area of research in information economics now, as well as in our community. So one can see easily, if we take Gaussian random variables, x and theta Gaussian, and W is not there, sigma W is 0, you can easily see that there is no Nash equilibrium with affine G and H. And that you can easily show. You take an affine H and then find the best affine G, and take the best an affine G, find the best affine H. Is there a common point of intersection? There isn't. So, but does that mean that there is no solution? No. In fact, the main result of the Crawford and Sobel in 1982, for the case when X was not, didn't have infinite support, its distribution, it's a bounded support, is that all Nash equilibria for G and H are non-injective. They are quantized space, which was kind of a surprising result initially. And the structure of the solution is such that given the problem parameters, there exists an integer which depends on theta. And note that this is, theta is known because this is a deterministic bias, such that T, the transmitter, partitions his message space into n theta cells and sends quantized information. Now, why this, after thinking about it, why does it make sense? Well, it makes sense because what the, without any channel noise, what the transmitter is doing is transmitter is inserting some ambiguity into the transmission. And this ambiguity is done by essentially quantization, through quantization, instead of adding an additional additive noise. It turns out that if you have an additive noise, it doesn't solve that problem. So this is one way of convincing the other side that they are still estimating X, but to make sure that in the estimation for X, you have a bias. And the bias is inserted through this ambiguity, through this uncertainty that is brought into the problem. So that's that. So quantization, we have seen in information theory, communication, and so on, is generally appears when there's a rate constraint or channel noise. So in this case, none of these are there. And it's there because you want to mislead the other side. You want the other side to actually think that the true value of X is X plus theta instead of X. And one can show that this result actually holds for an arbitrary source and arbitrary distortion measure. Now, there was one open question, which was whether, what happens, this was all for, until recently, the results were for a finite support set for X. And the question was, what happens if there is an infinite support set? For example, if X is Gaussian, again, the deterministic bias. And Serdar and two of his colleagues, one student and one colleague in Turkey, this is a paper which will appear in TAC, maybe in 17, showed that it is still quantized based, okay, for that case, without the noise. And they also showed that in the multidimensional case, that's the interesting part. If you have multiple channels, multi-dimensional X, then the solution, there exists an affine Nash equilibrium. There could be quantized ones also, but in that case, there exists an affine Nash equilibrium, even though for the scalar problem, there doesn't exist. So now what one can show is that what happens if you bring in W, the noise? As I indicated, you have, in the absence of noise, the transmitter has to bring in some ambiguity into the transmission. Now, if there's noise, maybe you wouldn't need that ambiguity. One can actually show that with jointly Gaussian X and theta, with channel noise there actually exists affine Nash equilibria, but under some conditions. It's too complicated to give the conditions here. So therefore, what this shows is that assuming those conditions, the conditions are, this is not a vacuous set of conditions, depends on the parameters of the problem, so which depends on sigma W definitely. And so what this shows is that there is a structural discontinuity as sigma W goes to 0. These linear Nash equilibria disappear, and you only have quantized solutions. So the question is, what about the Stackelberg scenario now? Do we still have quantized solutions? Do we have linear solutions? Now, surprisingly, the Stackelberg equilibrium, again with x theta, theta in this case is a correlated, is a random quantity, but it of course applies to the case when theta is not a random quantity, is a deterministic bias also. And both with noise and without noise, one can actually show that the Stackelberg equilibrium is essentially unique. By essentially uniqueness, I mean there is a sign plus or minus. You can send a message either with a plus sign or with a minus sign, and that sign has to be transmitted to the other side. So this is for the linear quadratic Gaussian case, and this will appear in an proceedings of IEEE special issue article either later this year or early. And if anybody is interested, this paper has a lot more. It's also the communication information theoretic sort of inequalities bounds, as well as the side information, when we have side information, which I'll not be able to discuss it further. So there has been a surge of activity during the last 5 to 6 years on this, both in the information, the Stackelberg equilibrium. So finally, the economists realized that that is an interesting problem. That would be something. When we talked to Sobel, he hadn't thought about that Stackelberg hierarchical approach to that problem, and he surprisingly he didn't know about Witzenhausen's counterexample either. So that was a refreshing conversation. But several other here I have given some selected papers. The Journal of Political Economy, American Economic Review in 2011. And we have one in the Information Theory Workshop in 2015, and this is Serdar's paper, which is the title, which, as I indicated, will appear in 2017. So there's a lot of activity, and I have just a sample papers here, and the list is growing. So so I may not have time to go over the proof, but this is just to show you what the structure of the solution is like. If you can take the expected value of x squared to be 1 without any loss of generality, theta squared to be r, and x theta, the correlation, to be rho, where r is larger than rho squared. And this is what the solution looks like. The transmitter has to use x plus a theta, and then the a is given by this expression, and then the u, of course, once this is linear, then this is the conditional mean of x given y, and which is definitely linear. Now, proving this is a different thing, and if we have the noisy channel, which means in that case, if you have the noisy channel, then you have to introduce a power constraint here for U0. And turns out that, note that the G sub S in this case does not depend on the noise variance. So whether you have a noise or not doesn't make any difference as far as the transmitter goes. It's still in the same form. There is an additional K here, and that K takes care of the power constraint. Okay? So there are the proof uses, the proof is in the paper. It uses two tools from statistics and information theory. One is the functional representation lemma, and the other one is the maximal correlation coefficient. So I'm not going to, I'm running out of time, so I have the sketch of the proof, but for those of you interested, I can send you the paper. Now, there are several extensions and variations of this. One is strategic communication with side information at the receiver. And this was recently presented at the Information Theory Symposium in Barcelona. So what is this problem? You have the receiver has additional information. This is known as the side information, V, which is quite common in information theory, these types of formulations, where V is correlated with X and possibly also with theta, could be correlated. And so therefore the G is a function of X theta, but the difference here is that U1, H is not just a function of Y, but it's also a function of V. Okay, so the same cost function. So what we can show is that for the noiseless channel, it's still a linear Stackelberg equilibrium. And if the side information is available, V is also available at the transmitter and still in the noiseless channel, the solution is the same. But with noisy channel, if the side information is available only at the receiver, then we have linear Stackelberg equilibrium under some conditions, whereas this is in contrast with the non-strategic version when there is no linear optimal solution. It's a much more complicated one. The Weiner was one of the people who has looked into that problem. Okay, so there is quite a difference between the Stackelberg formulation here and what solution it generates and the non-strategic version of this. And then there is another extension or variation, and this is information transmission with privacy constraints, and this was presented at the CDC in 2015. So let me just, I won't spend that much time on this, but just to show you that there are so many, it's such a rich class of problems that one can formulate, and some of them actually collapse to the same problem formulation which I discussed earlier and has the same type of solution. So in this case, both players or both decision makers have the same cost. They have a common cost, U1 minus X. So there is no theta entering here. But where theta enters, this is the privacy parameter or random variable. The transmitter wants to make sure that that as little as possible information is relayed to the receiver on theta. So one way of formulating this is to say, well, the only way R can find about theta is by forming, say, the conditional expectation of theta given y. And so what you want is this distortion to be larger than some bound, d sub p. So this is the privacy constraint. And again, in this case, now note that this may look like it's a team problem, but it's not a team problem because only one of the team members is in charge of making sure that this inequality is satisfied. So it is a game problem again. And the problem is to find a GS that maximizes this, subject such that this holds, where HS minimizes JR uniquely for all G. Okay, so and we can convert that problem into one that I just discussed earlier, and the solution turns out to be linear. Okay, and there are several. This is my last slide. There are many other sort of possible extensions of this. The multi-agent settings. What if there are multiple, as I gave in the example where the residents of a certain community sending information, so it's not only one of them, they may all share the same theta because they have the same, they want to mislead the receiver in the same way, or they may have different theta. So this asymptotic agreement types of things and so on definitely would be valid here. And then the networking environments, and then extending this to also multi-stage problems, which Serdar is looking into, and we have some work also on that. So I think it's exactly this. So congratulations, Thomas.
We are in the same team and so on and so forth. You may have communication, how we communicate, and then in between is where you extract information and models and et cetera, et cetera. And it is the interplay between these graphs which are annotated by